Hello everyone and welcome to this new episode of our tutorial series on Salome Mecha. In this video we are going to see how to create the geometry of a valve using the Shaper module. Let's go ahead and open it up from the Salome Mecha interface. As Shaper is launched, a first part is created, and I need to define the overall size of the view. Then I get to select the plane within which the first sketch will be created. This is actually going to be the generatrix of the upper parts of our valve. The first step is to create a rough freehand sketch that would be later adjusted through the constraints such as the ones that you see on the right hand side panel. So here I'm using a horizontal distance constraint in order to adjust the position of the bottom left point here. Now I'll carry on and do the same thing for the next point and the next point. Now I'd like to round the corner, so I'll go ahead and use the fillet tool here. I'll adjust its radius to a certain value. And now with this final length adjustment, the sketch will turn green, which means it is fully defined and constrained. Now let's go ahead and create the second sketch, which is the generatrix of the bottom part of the valve's body. Same logic here, a rough freehand drawing that will be adjusted later. You can also rely on the previous sketch for the edges where the two parts connect. So I'm using the same tools with different options. For instance, this arc here with the tangent point option. And as the contour is closed, I will use the constraint tools in order to adjust it once again. And with the last dimension, the sketch turns green, which means it is fully constrained and defined. Now that I'm done with both sketches, I'll step up to the next stage. And the idea is to create a 3D part by revolving this sketch around the z-axis. So this is the upper part of the valve. Now I'll go ahead and do the same thing for the lower part. And this is the result of both revolution operations. At this point, we come to a really useful feature, the parameters table. It lets you input your parameters as either expressions or direct values. In this scenario, we'll define the 4 parameters that will be accessible throughout all operations in part 1, allowing us to maintain a consistent and parametrically controlled workflow. For instance, if I go back to my sketch 1, you can see that if I remove this dimension here, I could easily replace it with my parameter that I just defined within the parameters section. So instead of having this hard-coded value, I can type in my variable name and it will give it the corresponding value. Now let's do the same thing for sketch 2, as it also depends on the external valve radius. And so the same way we did before, we're going to replace this value with the variable name. If I go back to the parameters table, I'll be able to modify the value of the valve's external radius, and as soon as I do that, it will immediately update and affect my geometry. The next step will be to create the holes where the studs will be placed. First thing, I'll need to define a point, which is the center of this edge here, and by the way, the center of the first hole. And I'm going to create the stud by making an extrusion from this point to form a line segment. And it will rely on the previously defined parameter, which is the stud's length. From there, I will generate the rest of the studs using the angular copy feature. The first segment is already selected. I'll select the revolving axis and finally the number of studs I want to copy. At this point, the 12 studs are created, and I would like to split them using the 3D geometry. Each stud is divided into 3 sections. The top part connects to the upper body of the valve, and the bottom part connects to the lower body, which is why we've segmented them this way. At this point, you'll notice that only the studs remain, and that's completely normal. It is just how the split operation works. It removes the original 3D parts we used as tools. Now the trick is figuring out how to get them back, and I'll show you how to do that. So right click on split one and then recover. And now I get to choose the parts that I want to recover. Now the next step is to drill the holes for the 12 studs that I've made. To do this, we'll start by creating a new sketch on this surface. Draw the base circle for the first stud hole, resize it, and then use the angular copy tool to replicate it for all 12 studs. Once the sketch is ready, I'm going to use it to perform an extrusion cut using this tool here. Let's select the sketch, set the drilling depth that we defined earlier, and then choose the 3D body we want to cut, in this case the upper and lower parts of the valve that we recovered. Now let's head back to our parameters table and define one final parameter to help us position the horizontal hole relative to the vertical axis. Now I'm able to create a new point which will have as a z coordinate the variable I just created. As the point belongs to the internal axis, I will need to use the transparency feature in order to see it. To make things clear, here's what we're aiming for: two concentric horizontal holes on the vertical cylinder. We'll start by sketching the red circle on the right, and we'll use its center to correctly position the base circle for the larger blue one. Let's see how to build this. From this point, I'm going to create a plane whose normal is the x-axis. And let's use this plane as a basis for the next sketch. I'll begin by creating the circle that forms the base for the narrow internal hole, with a radius of 0.002. Actually, what we're doing is using the center of the narrow hole circle that we have already created. By extruding from that point, we'll accurately position the center for the outer hole circle as well. So the result of extruding that point along the x-axis is a line. Now we're going to find where that line intersects the vertical cylinder. That intersection gives us the center point for the new circle that forms the base of the outer hole. After the split, the upper part of the valve disappears. That's normal as it was used in the operation. To get it back quickly, just right-click on the split operation, choose Recovery, select the upper part, and click Validate, and that's it. Now we're going to use that point of intersection as a basis for the new plane. Now click on Sketch and create the base circle for the outer hole. Now let's actually use it to drill the hole using the cut feature. I'm going to select the body I'm cutting from, define the distance, and validate. Now I'm going to create a fillet to round off the corner. Now we are going to see the last feature, which is group creation. Click on Feature and then Group. The first example here is to create a planar face that represents the top of the vertical cylinder. We'll use this face later on for calculations because we want to apply a background effect to it. The second example is a volume group that represents the top part of the valve that we will call the hat. Then we will do the same thing with the lower part, which is the body. Now for this example, we're going to select certain faces. To do that, let's first hide the lower part of the valve. Once we do, you'll see these faces are now accessible. They are part of the upper section, and this is where we are going to apply the pressure load. I'm going to use the rotation feature here in order to access these internal faces. And the last ones I'm going to select here are those related to the leak hole. One last example here is creating a linear group for the stud. I'm gonna need to hide everything but the studs, and for this I'm simply going to select the three entities that form the stud, and that's it. And at this point I will just be repeating the same operation for all studs. Finally, once we have created all the groups, this is what your construction tree should look like. That brings us to the end of the video. I hope it was helpful and thanks for watching.